Okay, so now we know what the first law of thermodynamics is. We also know what the second law of thermodynamics is. So we'll just quickly try and combine these two equations because it's a really interesting thing to do. And this will help us in some understanding about the chemical processes, okay? So we know the first law is dq minus dw, and we have to keep in mind the sign conventions. Expansion is positive work in here. So we know this, and we also know there's another, so this is the first law, and with the second law we know ds is dq by t for an irreversible process, okay? And then we'll, so in the second law is this is basically true for any irreversible process too, okay? So ds, so dq then becomes tds, right? So dq becomes tds, and we'll use this to put it in here. So this then becomes dE becomes TdS, right? And dW is basically P del V, right? We know this from before. So this is the combined first and second law. So this is combined first plus second law of thermodynamics, okay? Really simple, but really important. All right, so now like we defined the quantity H, which was basically E plus PV previously. Now let's define another quantity, which is E plus PV minus TS. Now this is the Gibbs free energy. Why did we do this? All right, we did this for a good reason, because this, as we know, is enthalpy, right? E plus PV is basically enthalpy. So in here, what we did, we combined two very important variables in thermodynamics. We combined the enthalpy and we are combining the entropy. So that is the reason we are coming up with this fascinating equation, okay? Now, if we differentiate it, what we'll get is delta G, delta H, and using the product law to differentiate this, we get this. Now, for an isothermal process, this thing becomes 0, and we can write this. Now, this becomes an extremely important reaction that you'll be studying in chemistry in general. So this is the Gibbs free energy. It's basically the available energy of any system, the Gibbs free energy. And the change in sign gives you important implications because, all right, so because there are certain reactions that can have, so this delta H is the change in enthalpy, right? Because you know that delta H can be positive for an endothermic reaction and negative for an exothermic reaction. Now, delta S can be positive and negative both ways because there can be a change in entropy of the system. There can be a decrease in entropy in the system. So you can have like delta S and delta H changing signs. But so neither of them individually define the spontaneity of the reaction. Like individually they cannot. They can give you some idea. Like, okay, in a spontaneous reaction, okay, this might happen, but this is alone, entropy or enthalpy cannot give you the exact measure. So that is why this equation becomes so important, in which we combine the effects of enthalpy and entropy, and then we are trying to see, then we are trying to guess, or then we are trying to actually see how we can, what we can say about the spontaneity of any reaction. All right, so keeping this in mind, this being true for any isothermal process, let's try and see some examples, right? So what if? Now, for a spontaneous reaction, the delta G should be negative, right? Delta G should be less than 0 for a spontaneous reaction. the delta G should be less than 0. Delta G is 0 for an equilibrium process, and delta G is if delta G is greater than 0, that means the reaction is not possible spontaneously on its own. So this is extremely important. So we would want to know, if we want to know whether a reaction is possible or not, we would want to see what the delta G of the reaction is like. So you can calculate the delta G using the similar formula that using an analogous formula that we used to calculate the delta H earlier, which could be just the delta G of any reaction would be the summation of the delta G of formation of the products minus of the reactants. You can do this, but what if you do not have this information and you just have information about the delta H and delta S of the reaction? Then can you say something about the type of spontaneity that the reaction might have? Yeah, okay, let's try. So if you have a delta H negative reaction, that means this is an exothermic reaction, and you have the same reaction has a positive delta S value. You see, when you use this equation, we can see that delta G is always negative in this case. If it's always negative, that means any reaction which is an exothermic and leads and brings about a positive change in the entropy is always negative. It does not depend upon the temperature. It will always be a spontaneous reaction. On the flip side, if you have an endothermic reaction which brings about a negative change in the delta S, the delta G is always positive. It's always positive, always positive. And that means this kind of reaction will never be spontaneous on its own. Okay? Now, any reaction in between, in between these cases, they become interesting, right? So let's assume that, okay, delta H is still negative, but what if delta S is also negative? Now you see, when you have delta S negative at higher temperatures, this whole term becomes more positive, right? This whole term becomes, this negative and this negative will cancel each other. This whole thing becomes more positive. So if you have higher temperatures, this whole thing tends to increase delta G, increasing the free energy. That means this kind of reaction will be spontaneous at low temperatures only, because at low temperatures there is a chance that this term will be less than the value of this term, and delta H being negative will kind of overpower and still give the delta G a negative sign. And just the opposite of this, if you have a delta H of positive and a delta S of positive, then this reaction will be spontaneous at higher temperatures. Okay? So this is the basic understanding of the Gibbs free energy. So when any reaction, if it is producing a delta G of negative, that means the reaction will be spontaneous. If it is producing a delta G of positive delta G, that means that the reaction will not be spontaneous. And if the delta G is 0, that means the reaction is at equilibrium. Now, having said that, now let's start to think about what equilibrium exactly means.